Good morning, everyone. So I will talk about MRI, and the main content of the talk will be dynamic contrast-enhanced MRI, because that is the main technology that we use in MRI to derive arterial or plasma input functions. I will show examples of the work that is being done on tumor staging diagnosis, because for that particular application, this technology is primarily used. And I'll also show work in our own group from measurements of myocardial perfusion using this technology. And of course, in the end, I will give you some hints for recent developments. So the MRI-based arterial or plasma input functions are mainly used to get tissue perfusion information and to measure tumor vascular permeability. In MRI, there's two main perfusion methods. The first one is arterial spin labeling, which I will not talk about because that is really not very much related to input function measurements. So I'll spend most of my time on dynamic contrast-enhanced MRI, which is used a lot for plasma input function measurements. So what do we do in DCE-MRI? We inject a bolus of an MRI contrast agent, in most cases a paramagnetic MRI contrast agents, and then we have a very dynamic rapid scanning procedure, which is to track the passage of the contrast agents through the tissues of interest. And it could, for example, be a tumor, but of course also blood vessels, because all the input function measurements I will be talking about are really image derived. It's actually, in MRI terms, it's a relatively old technology, because already when the first MRI contrast agent became available in the 80s, people started to do this work. But only a lot more recently has this really turned into perfusion imaging, because in order to do that, you really need very rapid scanning. And of course, that was not possible in these early times. So there's two main scan protocols that we have to do this DCE-MRI. One is called T2 star weighted MRI, or also dynamic susceptibility contrast enhanced MRI. DCE-MRI for short. That was initially the most used technique, but I'll briefly hint to why this is no longer very popular for this particular applications. And the other one is T1 weighted scanning that is used mostly now. So what do we do? To get it straight, we inject as a bolus an MRI contrast agent, and then we track, for example, in the brain, in this particular example, its passage, first passage, and to get this dynamic data and then try to derive perfusion and information, whatever you would like to know. So this old technology of T2 star weighted MRI and DCE-MRI, abbreviated, has been used a lot to do so-called bolus tracking. Here on the top you can see raw data, where initially the image intensity is high and then it goes down because of this transient passage of the bolus of the contrast agent to the brain. Now we can convert that into concentration images, relative concentration images. So you can see that the effect is quite strong. So in principle, this technology is quite sensitive, but there's a lot of issues there, because this technology suffers a lot from quantification issues. And actually, there's a very nice paper, a recent review in Animal and Biomedicine, that sums up to 39 issues sort of that are there. Not all complicating issues, but at least things one needs to think about when applying this particular technology. So I think this already illustrates why now this new technology, or I shouldn't say new, but other technology of T1 based DCE-MRI is a lot more popular. So I'll focus on that now, talk about the MRI contrast agent, how we relate signal change to local contrast agent concentration, because that is really a key issue in this field, like always. And then, of course, we'll also talk a bit about data acquisition and analysis. So this is the sort of the mother of all MRI contrast agents. It's gallium DTPA. It's been there since the 80s. And it's one of the examples of the agents that are used a lot. It has 7 unpaired electrons, this gallium ion that is in the center of the chelate. And that has a very strong effect on nearby water protons, in the sense that it shortens its relaxation time T1. I'll explain that in a bit more in a minute. Now it's a small molecule, so it's cleared rapidly by the kidney. So we can use it really in a very, very safe way. So I indicated already it's not just gallium DDPA, it's also gallium DOTE and other compounds that can be used for this particular type of application. So what does it do? It shortens the local T1 relaxation time, and T1, you should understand, is one of the key contrast parameters in MRI that we make use of a lot. And so depending on the experimental setting, we could, for example, have a situation that the signal would be sensitive to changes in T1, such that if we would initially have a relatively long T1, and that the signal would be relatively low in the scan, and then when the condensation arrives in the tissue, because of shortening of T1, we would get an enormous shoot up in signal intensity because of this local shortening of the T1. So that's a very sensitive way of detecting the presence of the material. And it's actually used a lot. In approximately 30-40% of MRI scans are made with contrast agent injection. So for example, here you can see in the second scan from the left, and that the injection of the material leads in this mouse heart with an infarction to a very nice light up of the infarct region, whereas the non-infarct tissue is not highlighted so much. So we can deduce from this infarct size. But of course, in terms of signal change and local condensation concentration, this particular scan does not provide that sort of numbers. So now I want to come to real quantification approaches, input function measurements for tumor characterization. The tumor actually, it's used a lot for that, is a special case, because if we inject the contrast material into the bloodstream, in normal blood vessels it will not extravasate very rapidly, but in the tumor, because of incomplete endothelial lining, we will see very rapid extravasation. So the material goes into the extravascular, extracellular compartment, not into the tumor cells. So that's why when we apply this sort of contrast materials in a tumor setting, we see very fast and high levels of enhancement, especially in malignant tumors. And that's actually the key success factor for DCE-MRI in the clinic. So we see enhancement patterns, well-perfused tissues in the tumor, they go up quickly, and then that's very often a sign for malignancy, whereas purely perfused regions do not show that. Of course, although information of this type is very rich already, of course it's semi-quantitative. We only get sort of pattern recognition and not really quantitative information on perfusion or vascular permeability. So for that we need to convert the dynamic MRI data to contrast agent concentration time curves. And we'll show now how we do this at the level of the plasma, the blood, using MRI, so image-based deriving the arterial input function. So I want to show you some phantom data for that first. Actually, this is very important data in a 2011 paper from a Dutch group that compared MRI to CT in terms of the linearity of the signal readout to the concentration of the contrast agent. I want to show you, draw your attention to this panel first. So this is the concentration of the agent, contrast agent that was put in to the phantom, and this is the estimated readout of the concentration. And then you can see that if we base our MRI analysis on the magnitude of the MRI signal, I will explain in a minute what that is, then we get a very strong non-linearity at higher condensation concentration. So that's not good. So we cannot use this particular approach very reliably to estimate the local condensation concentration. But if we go to the phase of the MRI signal instead, you can see that we get a beautiful one-to-one correspondence and linearity also at higher concentrations. So this advocates the phase of the MRI signal for this particular purpose. And by comparison, of course, CT with its Hounsfield units supplies a very good linearity between the concentration of the CT agent and the signal that one gets. Now, after the phantom studies, these are the studies in the femoral artery, in vivo, in man, again comparing MRI at 3 Tesla to CT, and you can see that the arterial input function derived from CT closely matches that observed by MRI when basing ourselves on the phase of the MRI signal, but not when using the magnitude of the MRI signal. And again, showing that and we better use the phase of the MRI signal. So what is that, the phase? Well, the whole story comes about because the MRI signal is complex. We have a real and imaginary part, and the phase is then basically the balance between the two. Now it turns out a lot of studies being done that the phase change brought about by the contrast agent, when measured with MRI, is nicely linear with concentration and is not affected by many of the other things we have out there that affect, for example, the magnitude of the signal very much. So again, it's basically pointing to the very high utility of phase imaging. So how do we measure this? Well, basically what we want to have in the plasma is this concentration of the contrast agent. For that we measure changes in the phase that are brought about by its passage. And then we need a sort of a calibration coefficient, the phase coefficient, that we can partly measure and partly know from literature. So I don't want to spend a lot of time on this. We have knowledge of that, we measure this, so we get, as a function of time, the condensation concentration in the plasma. So then, I want to show an example now of recent work in mice at high field where the susceptibility effect, so the readout of the phase change, is very sensitive. In comparison, in the mouse iliac artery measurements of signal magnitude, times 0 is here the moment of injection of contrast agent. Comparing magnitude to signal phase, you can see that indeed signal phase nicely behaves as an arterial input function, whereas amplitude does not. So far so good, and then we have this formula relating the phase change to contrast agent concentration in the artery. Then, taking into account the hematocrit, we convert this to the plasma contrast agent concentration, and then by fitting we derive the arterial or plasma input function. An example of which is shown here, typical values in mice for a gadolinium chelate. So now we have this plasma input function, of course we need to worry about the tissue response because we want to learn about the tissue. It's not the AIF or PIF is not really of interest by itself. We want to learn about the tissue. So now we need to play the trick that we are going to quantify the condensation concentration in the tissue compartment, because then combined with the AIF, then we'll be able to get perfusion or vascular permeability in the case of tumor. So for that, it turns out that the R1 contrast parameter, a key contrast parameter in MRI, is most attractive because changes in R1 scale linearly with condensation concentration. So how is this done? Very simple formula. This is the intrinsic longitudinal relaxation rate that we can measure. This is the value that we measure after condensation concentration, injection, and then having this proportionality constant, the ionic or molar relaxivity that we know, we can calculate the condensation concentration over time, like according to this formula. So I will be quick on this. So basically what we do, we know the signal response in MRI very well, so we can deduce from the dynamics of the signal changes in T1 and then compute the total condensation concentration in the tissue, knowing the plasma one, and we can then do two-compartment modeling. Very similar to what Adrian has been describing, so don't want to go into this at length. And one of the very important parameters that we extract from modeling like this is called the extended Tofts-Keating model in MRI, is this K-trans parameter. That's the transfer rate constant of condensations transfer from the plasma into the extravascular extracellular compartment. And it turns out that this is a very nice parameter to do tumor characterization. So here's an example, a tumor growing, a glioblastoma in mouse brain, in the setting of anti-VEGF therapy, anti-vascular therapy. You can see that the control tumor grows, but also the treated tumor grows. But there is vascular normalization because it turns out that if we do the K-trans mapping, according to technology that I just showed, you can see that as compared to the control animal, the K-trans values, so the permeability, leakage of the condensation into the tissue, a measure of vascular permeability is down a lot. So this is a sign of vascular normalization brought about by this therapy. And the self-same technology is used a lot in the clinic too. So here you see, for example, also in the setting of anti-VEGF therapy, scans of a patient at very regular times. You can see that already at day 1 into the therapy, the K-trans values are down a lot, again pointing to vascular normalization. And so this technology is strong, I think, both in the preclinical and the clinical setting. So this is tumor, and I want to go to recent studies that we did in the heart of mice. Quite challenging setting because the heart is ticking 600 beats per minute, so we need to be fast in our MRI scanning too. So this is the procedure that we use. So we use this setup for first pass perfusion MRI to quantify perfusion in the left ventricular tissue by injection of a contrast agent. So we have a power injector delivering contrast agent material in a very controlled way. We have a number of different infusion lines going into the animal, and so that via the tail we have vein we can deliver an appropriate amount of contrast agent. And then I indicated already we need to be fast. So we have now approximately 4 images per second in the heart by using a so-called accelerated saturation recovery technique that is sensitive to the presence of the contrast agent. So we get images 3 to 4 times per second. And then in this particular experiment, I'm not sure whether this I don't think this holds for the other techniques, but for MRI, we can get saturation of the signal chains at high concentration of contrast agent. So that's why in this particular case, we use a dual bolus approach. We first have a low quantity pre-bolus that we can use to derive the arterial input function from the left ventricular blood. And then we give a full bolus that allows us to accurately analyze the tissue response. And the combination of the two is then used for mathematical modeling to get perfusion values in the left ventricle. So here you see typical scans of the pre-bolus experiment, where initially the signal is saturated very much, and then we see contrast agent arrival in the right ventricular blood, then in the left ventricular blood, and then in the tissue a bit. If we use the pre-bolus, you can see pretty much a lot in the full bolus. So this one is used for arterial input function modeling, and this one is then used to reduce the signal response from the tissue in order to derive really perfusion values at the left ventricular material. So I already indicated that the pre-bolus is used first because then we are in a linear range of contrast agent versus signal intensity relationship. Whereas if we go to the high concentration of the full bolus, then the signal will be saturated. But we need this in order to get a full tissue response. So use this one now to predict the arterial input function that would hold under the conditions of the full bolus, because we need that in order to do the perfusion analysis. So first of all, we needed to prove, that's very important to all of this, that there's linearity between the signal change and the contrast agent concentration, also for the pre-bolus. So for that we did a lot of experiments, and you can see indeed that if we take different quantities of the contrast material, then the response in the left ventricular blood, the source of the input function, is indeed beautifully linear to the quantity of contrast material. So this condition is fulfilled. So then, in order to construct the arterial plasma input function, under conditions of the full bolus, what we did was we constructed a full PIF from 4 time-shifted pre-boluses using the mean transit time of the full bolus to match the two. And then we get the arterial input function that holds under conditions of the full bolus. If we do that, we get the response at the level of the left ventricular tissue. We do modeling using Fermi-constrained deconvolution, which I don't want to go into, that is typically used in this particular type of application in MRI. And then we get perfusion values quantified in mils per minute per gram, which are around 8 or so in this mouse left ventricle. Very reproducible robust technology in our hands. And we use this, for example, now in the setting of heart failure studies. Heart failure leads to hypertrophy of the heart, as you can see, with very big hearts as compared to the control mice. And we hypothesized that early on in the development of this disorder, early perfusion changes play an important role. And indeed, if we go into the animals 1 week after surgery for induction of heart failure, you can see a tremendous drop in the perfusion values that we think are key to this particular pathology. So this already has been used in human studies for a very long time. So this is actually an example of reverse translation, and where this technology was available in the human setting, it now only recently became available in the preclinical setting. And the reason for that is that it's a lot more easier to be done in the human setting because we have lower rates, bigger volumes, etc., etc. Actually, recently was a very nice paper where in a big animal, a dog, myocardium, MRI was compared to gold standard microsphere measurements, of course, invasive technology, and showing a beautiful one-to-one correspondence between MRI-based perfusion measurements and these microsphere measurements. So, a pretty robust technology, it seems. So, what is this technology used elsewhere in the pathology settings? Well, we see it a lot in cardiovascular diseases, plaque characterization, abdominal aorta aneurysms, in general a lot in inflammation because there's a fast influx of condensations in that particular setting, but also, for example, to probe dysfunction of the blood-brain barrier. What new developments are there? Well, one is related to the fact that it's not trivial to always measure the arterial input function in an artery close to the tissue of interest. So that's why some people have resorted, Mark already mentioned this, to population averaged PIFs, but that's, I think, is suboptimal. Or people try to derive now the input functions from measured tissue concentration time curves. Like, for example, reference region approaches, but I think there's a lot of hope for a new technology that's called Monte Carlo blind estimation technology that's, for example, developed by Matthias Schabel in Portland, Oregon. So with that, I want to sum up. I think for MRI to do this input function measurements, we need a very high temporal and spatial resolution. Well, the technology is capable of doing that. I try to indicate that in order to get these input function measurements, the magnitude approach is not very good. The phase-based approach is preferred. And we see main applications in tissue perfusion, permeability of tumor vasculature, and in inflammation imaging. With that, I want to thank these colleagues for providing me with slides, because the field is very broad, so we needed some input there. I want to thank the people indicated in bold in my group that contribute to this type of work in Eindhoven. And I want to thank these institutions for funding our work. I want to thank you for your kind attention.